Alright, let's take a look at one more example resonance frequency problem. This is a fairly straightforward process, so I'll just try doing one example and then sort of leave you to your own devices. So let's suppose that we have a mass spring damper system with a mass of 2, a damping coefficient of 1/2, and a spring constant of 5, and we want to find the practical resonance frequency of the system. So the first thing I'll do is I'll write down the corresponding ODE that governs the motion of the system. That would be 2y double prime plus 1/2 y prime plus 5y equals, now when we're looking for a practical resonance frequency, that means we're driving the system with some periodic driving force. And again, we want to find the driving frequency that will result in the longest long-term amplitude of oscillation. So first I'll write down the ODE. 2, I'll find the steady state portion of the solution. So that's the portion of the solution that tells me the long-term behavior of the system. So let's see, I want to desolve 2 times y double prime of t plus 0.5 times y prime of t. Sorry about that. Let me flip this up quick. Plus 5 times y of t equals cosine of omega times t. We'll desolve this, and now we have the steady state portion of the solution sitting right here. And this tells us the long-term behavior of the system, the long-term displacement, if we apply a forcing frequency that has frequency omega. So let's go ahead and copy that down. So we've written down the steady state solution of the system. Let's go ahead and we'll rewrite it in a form that's more suitable for us. Yp is equal to, and let's remember how this goes. We'll need to factor out the cosine and sine terms. Let's see. Oh. You need a comma there. So we factored those terms. Let's go ahead and rewrite this. We need the amplitude, remember. A is equal to, it's the square root of this first coefficient squared plus the second coefficient squared. I like to just go ahead and copy this whole first term, paste it in here. Don't forget, it's just the coefficient we want. I only copied the whole thing because it was easy. Now I need this part. And don't forget to delete the sign. So there's your amplitude. Let's go ahead and simplify it. Alright, so let's go ahead and copy down the amplitude here. A steady state solution in a form that's easier to work with. Here we have the amplitude A that depends on omega, and we have the phase shift, which we haven't calculated, we just said it's there. So the amplitude of oscillation, which depends on omega, is 2 times the square root of 1 over 100 minus 79 omega squared plus 16 omega to the 4th. If someone said just graphically go ahead and find for us the resonance frequency, we could plot that thing and see where its max is. And it looks like it's right around omega equals, well, 1.8 or something like that. We could, of course, zoom in if we wanted to. If we zoom in, let's see, maybe around 1.6, so maybe I graph this from 0 to 1.6, and we could just continue doing this. It looks like it's around about 1.57. If we want to find it exactly, we could just set the derivative of a equal to 0 and see what we get. So we could solve and we'll see that it's that it is 1/8 square root of 158. We could eval f that. And get 1.5712 and change. So that's how we find our resonance frequency.